Bismillah ar-Rahman ar-Rahim. Welcome back to our course, Deep Learning for Computer Vision. Today we are going to continue our work on the deep learning part, and we'll tackle and talk about popular convolutional neural networks. This includes the VGG versions, the GoogleNet, the ResNet versions, and other well-known CNNs. So let's go to our lecture and continue our work using these lecture slides. So, as clear from the title, we are going to work on popular deep CNN networks. Here we can see that we'll start with an overview. We'll talk about the VGGNet, the GoogleNet, then we'll talk about the ResNets, maybe some other popular networks and popular datasets are going to be discussed, and we'll talk about it as a sort of brainstorming in this direction of work on deep learning. This overview was selected or taken from the 2018 year. Now, if you look at this graph, you can see almost all CNNs, deep learning neural networks, or CNNs that were developed at that time. The results are shown in a two-dimensional graph, having on the y-axis the top one accuracy. Let's take this pen now. So here we are going to talk about the top one accuracy. Of course, the top one accuracy gives you information about the predicted class of the from the input actual data that lies in within the 1% accuracy. Of course, sometimes we may have up to 1,000 classes, and when we talk about 1% accuracy, it means that about 100 classes, the highest 100 classes are taken from these great number of classes in this situation. When we go to the x dimension or the x coordinate, we can read there the operational or the operations in giga flops. So what is a flop? What are the flops? What are the flops? So what is this term flops? It's the floating point operation per second. Floating point operation per second. It's a measure of that gives us the performance of the ability of a computer processor. Of course, here this type of measures represents it's actually a raw measure that does not every time reflect the exact case when we deal with neural networks. However, it gives us an indication about the computational time required for providing or performing the training operation using the given network. Also, we can here see that the circles, why the circles are small and some are large, it represents the number of parameters. So the number of learnables or number of parameters that are going to be learned within the system. Now, as you see also, you can see that the type or the year of the it comes up with time, and you can see also. Let's have a zoom because it's not very clear now I think for you. Zoom this graph. So if we start with, let's say, from the beginning here, so this and this. So if you look at these networks, if we start with our previous version, the initial or the first linear neural network, deep learning neural network, it was the AlexNet. I see that its circle or the size of the circle here represents something like this one, and we know that the AlexNet is about 62 million flops or mega flops. If you go further up in the graph, you can see that we have other systems and neural networks, deep neural networks, like the Google Net. Here we can see the Google Net. Okay, you can see here VGG 18, 11, 13, 16, and 19. So as you go further, you can see how the it's clear, for example, here for VGGs that it requires more complications or more complexity, and processing or number of layer numbers is higher than, for example, with the Google Net. We can also see the ResNet. Can see also the ResNet, mobile net version 1, mobile net version 2, and as we go up, we can see that the accuracy increased and improved. And when we have a larger size of the circle, this means that we are dealing with wider or higher computational cost with more and more learnable parameters. And we may reach for new types, the trendy, let's say trendy deep neural networks or deep CNNs, like these days you can see like SENet, NASNet, NASNet, A large, SENet 154. We can see also Inception ResNet. If you look at this here, let's have a pen now. So Inception ResNet version 2, Inception version 4. You can see also SE ResNet XT. All these neural networks have a high performance with, as you see that when we go higher and with time, we see that the programmers and the scientists are producing new networks that are more compact, with lower complexity, and with better performance in general. However, if you look here, for example, when you go to select one of these, let's say, networks like this one or this one, you can see that the computation cost is high in terms of the number of G flops or flops in this case. And also the number of learnable parameters is varying according to the circle size, as I mentioned before. So let's go now and see some examples on these networks. As a reminder, the LXNet, as here, it was produced and it was the first deep neural network that opened the door of the deep network learning and applications. It is consisted of 8 layers. We have convolution layers with max pooling. We have 4 fully connected layers in case of the 4, including the output from the third FC. So in general, it has 8 layers. The number of learnable parameters about 62.4 mega learnables or learn parameters. Okay, it was trained on the ImageNet data store, and this is a very well-known data store having more than 2 million images for training. The parameters of the AlexNet are available free on some applications. I mean by the parameters, the W parameters, the weights and the basis for this network, and the structure is also available. You can find it on Python, in MATLAB also. Number of classes at the output is 1000 class for the output for image recognition and classification purposes. However, this system was at that time was difficult to implement it using the CUDA application or the CUDA processing type. Of course, the CUDA stands for Computer Unified Device architecture. It represents, or it is very closely related to the ability of the parallel processing platform of the computers. Of course, nowadays this issue is very simple and is affordable in most all of the even the personal computers. and it can be learned and trained very quickly according to the size of the input data set that you are applying to it. This was the invention that opened the door for all the deep neural networks and deep convolutional neural networks to work in this direction. So next, after a while, the VGGNet was produced in 2014, and it was a little bit different from the structure is the same as AlexNet, but with some specifications that were not included in the AlexNet. Now it was trained because it was invented later on. It was trained on four GPUs, and in parallel, and took 2 to 3 weeks. You believe in that? So the learning is very long and heavy task in applications. It's currently the most preferred choice because its training was done very effectively and can be used in what we call it transfer learning. What does that mean? You can take for example, the VGGNet trained on, let's say, the ImageNet dataset, the input, and apply it to another type of systems. In this case, of course, you just need to replace the input layer and the output, a few output layers in order to fit your data. For example, your input has 10,000 let's say data images or images in general, and the output class maybe not 1,000. It could be a little bit less. For example, 10 classes, 8 classes, whatever the number. You can just modify the softmax layer, the output layer, and the input layers, and apply it to your system and to your application. In this situation, you repeat the training, and it will take a shorter time because it has been trained on a very wide data set and very large data set, and it just need to calibrate or to fine-tune these parameters. This is called the transfer learning. We'll talk about it later on when we deal with MATLAB. However, it's just good to have good info about this, because you will not be able to, you are not going to repeat this for GPU for 2-3 weeks. You just need to take it and transfer to your own problem and work on that. Next, what we can do else? What about VGG? What is this VGG exactly? If you look at the image here, you can see that in the case of the VGG, we take the images as RGB of 3 layers of the size 224 by 224. And as you see that this is the structure of the network. If you look at this box or cube, it's a conventional block with ReLU activation function. So this one is, let's take another pen. Maybe we can take this one. So this is a conventional layer with ReLU. This one is also this one. These are also, as you see here, are all conventional layers. Of course, here we have a lot of layers. This is for the first part, for the convention plus ReLU activation layer. Next, we have a max pooling layer, which is as you hear, almost red color. This one is max pooling. This is also max pooling. This is also max pooling, and this one is also max pooling. Again, for the other layers, if you look at the fully connected layer with blue plus ReLU again, and we have a softmax. Finally, we get at the output an image of the output size as 1,000 classes. And for the softmax, we have one layer, and we have here 3 fully connected layers connected to the output, as usually done in deep learning. Okay, this is the main structure of the VGG net. It was called VGG 16. Mainly and similar to AlexNet, the convolution that was used in VGG was based on 3 by 3 convolution. So the convolution size was unified to be 3 by 3. This will give us this gives us a unified size for the kernel of convolution, and by this size in AlexNet we have 11 by 11. Oh, sorry, I'll take a pen. Okay, so it will be 11 by 11, 11 by 11, maybe also 7 by 7, etc. All these sizes are included. Now, in case of the VGNet, we have only 3 by 3 convolutional kernels, and this will help us to reduce the calculations, because when you increase the size of the kernel, you increase the calculations, and specifically when you have a stride of 1 s equals 1, so you repeat the process 9 times in case of 3 by 3, while you repeat the same processing or the dot product by 11 by 11 means that 121 times per pixel, and this is why we say that we reduce the size of the operation or of the processing. Now the weight configuration, so the network itself with its trained weights is available publicly, and can access it on MATLAB or also on in Python. You can just download this network easily. And it has now actually, because it's larger than AlexNet, it has almost double size of the AlexNet in the number of learnables, that reaches about 138 mega learnables or mega parameters. These are the main features of the VGNet, the first type of the VGNet. We have here two versions of the VGNet. The first one is what we call the VGG16. It contains 16 weight layers or learnable layers, and this is why we call it VGG16. While in VGG19 we have added, or they have added, the authors or the producers, 3 weighted layers or layers with weights. It is slightly better than VGG16 because it has more convolution layers and extra training or deeper learning in this situation. This is the most general form of the VGG16. So simply, as you see, let's have to zoom this one. So this is the input image applied to the network. The first, let's say, layer or combination of layers, we have convolution layer part 1. So we have 2 convolution layers followed by pooling. Next, we repeat the same as you see here in all cases. These blocks are repeated many times. So this is one of the features of the VGG in general, 16 and 19 for sure, that it looks like a small block that was stacked together to form the overall network. If you go now to the latest stages, you can see that we have 5 repeated stages with or blocks. Finally, we have FC, the fully connected layer 6, 7, and 8. We have 3 fully connected layers, and the output will be applied to the softmax layer with the classification layer at the output. So this is the main idea behind using the VGG 16 and 19. Okay. In this case, we have VG16, of course. Now let's compare AlexNet. The number of layers is smaller than VG16, and in the case of the VGG19, we have, let's say, a larger number by adding extra layers, convolution layers with real layers or activation layers. So this is about VGG16 and VGG19. You can use both. I would respect if you take VG16 because it is almost very well designed, and it gives you good output performance, and it reduces the time a little bit when compared with VG19. It depends on your application, of course. The other very well-known deep neural network or deep convolution neural network is the GoogleNet, where it was called earlier by Inception V1 or version 1. So the GoogleNet is a CNN inspired by the LUNet that was described in the previous lecture, with adding some novel elements, mainly what we call it the Inception module. Now, GoogleNet utilized also batch normalization. We discussed this issue in when we talked about the key elements in the CNN. One of the blocks is the batch normalization, and it is very useful in compacting the output of the layer between 0 and 1 in order to avoid different biases and different averages of the data points applied to the input. It also implements the RMS propagation or RMS organization tool. This will improve your deep neural network performance as a result, as will be explained later. In GoogleNet, we are going to use several very small convolutions like the VGGNet that reduces the size of the number of, let's say, the learnables, and this will be reduced from around 60 millions that was in case of using the AlexNet. I see that AlexNet was 62.4 to around 4 million parameters. This is on to the fact that we are using small convolution blocks, and we repeat this many times. This is one of the good features of the GoogleNet, and more we can have some other also information. The GoogleNet was let's say published by the team of GoogleNet, Christian Zigdy and his partners. They propose to have this in multiple parallel paths. This will, of course, when you use parallelism or parallelization, you are going to reduce the computational cost required to get the final answer using a shorter time. And this led to reduce for sure the time and to improve the performance. So at the same stage or the same layer in GoogleNet, it was actually very, very interesting to capture details at different levels, from fine grains or fine details up to large objects. And this was very interesting, actually, very intuitive in this direction because of this feature, what we call the inception feature. Now let's go and see what is the inception block in general. I'll try to explain it using this figure. So here, if you look at, for example, if we have an input, okay, here, suppose that we have an input of from previous or earlier layers obtained as 88 by 88 by 192 channels. Of course, this can be achieved from previous layers as a result of increasing the number of filters. Now, in case of applying the inception module, in its block diagram, or in its simplest case, we are going to do the following. We firstly apply max pooling layer, and this max pooling will be producing an output. Here, as you see, it will be 128 by, let's say, 28 by 28 by 32. This is due to applying the max pooling. If you go back to the output size as a max pooling, you can find this according to the rule that was described in the previous lecture also, which is the output will be equal to the input minus k plus 2s over plus 2p over s plus 1. And this will lead to reduce the size from 28 to, or to change it from 28 and keep it 28, but in the channel direction it will be reduced to 32 instead of 192. And this is caused due to the number of channels selected in this situation, or number of filters. Now, the second step is to apply 5 by 5 convolution, large convolution size, with a number of filters that is equal to 192. And this will give us this part, the red part, as you see here. Next, you can apply 3 by 3 convolution with the same number of filters, 192 filters. And we can apply, this is new for our case, which is 1 by 1 convolution. It was also discussed in the previous lecture. and it was, as I mentioned there, that it is used for dimensionality reduction, and it's a sort of matching between two different layers with consequent layers with different filters. Now, if you go at the total number of the output size, it will be 220, 256 with the dimensions in the spatial or in the XY, it will be 28 by 28 of course, by the number of channels 256. Of course, we are going to concatenate, depth concat in the direction of the channel in the third direction, all these combinations and apply it to as one block at the output. This block produced here is mainly, or it contains all required details about the various features in the input, let's say, feature map or matrix, where you can, using the 1 by 1 combination, you can concentrate on the channel direction, while in 3 by 3 you can concentrate on small sized objects. In 5 by 5 you can concentrate on larger objects. In the max pooling you are going to concentrate on the prominent feature points in the input, and all this together will help you in finding actually a combined output that may be very useful in next stages or next layers. Now, this model, what we have done here, this is similar to the explained figure in the previous slide. Now, we call this one as naive inception module. It's very simple. Now, in GoogleNet, it was modified this way. As you see here, if you look at the construction of the full inception, everywhere you have 1 by 1 conversion at all 4 branches. Of course, here, as you see, we first apply 1 by 1 convolution, then we apply next the 3 by 3 convolution, 5 by 5 convolution, and of course, before applying the 1 by convolution to the max pooling, we apply it first in order to keep the prominent features and not to lose these features by applying. If we switch this, we may get some problem in finding the important points in the feature map. So this is the full inception module in case of using it in our or in the GoogleNet configuration or architecture. We have some deeper look on this is the network in its layers, and we can see that these are the details at every layer in the GoogleNet. I think I can show this in MATLAB. I hope that I have it somewhere here. Yeah, this one. This is our let's say one layer. This this block is a depth concatenation layer from the previous layers. Now we apply. I try to zoom it a little bit if it's possible. Okay. So at the left-hand side here we have this connection. Here we have the first one. If you look here, we can see the details. Here we have convolution, the filter size 1 by 1. So it's a 1 by 1 convolution. Then followed by ReLU layer, then followed by a 2-dimensional convolution. In this case, we have 5 by 5 convolution. And finally, again, we have ReLU activation function. On the second branch, here we have the max pooling layer. So we have max pooling of the size 3 by 3. You can see it here. Also followed by convolution 1 by 1 convolution. A number of filters here is 64. Similar to the number of filters used here also, if you look at, yes, at this point, which is again 64. So these filters have this one and this one and this one have the same. We have here 5 by 5 convolution. Here we have 1 by 1 convolution, followed by the ReLU activation function. Here we have the convolution of 1 by 1, followed by ReLU, followed by 3 by 3 convolution with 224 filters, and followed by ReLU activation. And here we have this branch, we have 2D one by one directly, and this one will be the ReLU activation function. Of course, the GoogleNet has been modified many times, and you may find some different versions for this network. Finally, all these outputs will be combined and will be concatenated depth-wise in the direction of the channels in the third direction, and we'll continue and repeat the same process many times. As you see here, this is as you see here, we can see that the same block diagram, these small pieces are repeated many times. At least we can see here 3 layers or 3 let's say block layers in this situation. Let's go back to our presentation. So this, and it has been already discussed, this part. Finally, we can get the output softmax layer, and we may find somewhere we have added, or the GoogleNet has added a dropout layer. The dropout layer is very important in avoiding what we call it the overfitting, and this was discussed or described in the last lecture. You can go back and see the main concept behind using the dropout. In general, it was used to avoid overfitting and to improve the performance of the system. Here the total or the overall block diagram of the GoogleNet. These, as you see here, we can see the repetition behavior of these blocks. This 1, this is 2, this is 3, etc. Now, what about these new added layers, this one and this one? What are these layers here? We'll see this on the next slide. But in general, as you see that we are repeating small pieces or small blocks many times with inventing the inception idea of the model, inception model of the inception model into the interconnection of these small units or blocks, let's say. And this will give us better performance. Now for this network, if you look at these parts, we call this as the auxiliary classifier for training. So what it is used for and why it has been added. These small pieces are added for very important idea. So what do you think? In fact, the utilization of this block is done to push the useful gradients to lower layers, combat the vanishing gradient problem. So what does that mean? Now, when you have a deep neural network that is stacked, block stacked to each other, and the number of layers is high, sometimes this may produce a problem with the back propagation when dealing with the gradient calculation. When you calculate the gradient, it may be going to very small value, and we call it the situation when it occurs, it's a vanishing problem, vanishing gradient problem. Now, the main purpose in this situation is to get more control on the network by adding this auxiliary classifier for training. It contains these parts, we'll talk about it later on, and it's sort of an exit for the network to bypass or overcome the vanishing gradient problem or situation. So let's have a deeper look on this part. It's an intermediate stage or classifier that can be used to improve the performance. It contains, for sure, as you see here, simply you can see that we have here we have a 5x5 average pooling filter. The average pooling was also used by the VGG, by the GoogleNet, and was not used by the VGGNet. Also, so this is one of the good things that was used in GoogleNet. Again, one-by-one conversion, which is the inception, was also used here, and it contains one block in this situation in the auxiliary classifier with 128 filters. and two FC layers, fully connected layers that are used with an output of 1000 outputs, and a softmax layer for sure. And here with regularization softmax activation that was done in this situation. So uh, if you get some problem with the main branch due to the vanishing gradient problem, you can get this auxiliary or this exit for your output. Of course, this will increase the loss, and the total loss will be increased by a small value, which is about 0.3 in this case. So this is also one of the benefits of using the Google Net to correct or to take a control over the training process. And the of course, this part is used during training. The auxiliary classifier is used only during the training, while during the production or the testing, it is not used actually, and it is disconnected in some more or less from the network. Now, this is for the Google Net. So what next? What we can find next? Uh, for sure, here you can see this mistaken from the well-known video or movie. The question was, what next? And the answer was, we need to go deeper. And this is usually, we take it from this as a legend for our need for deep neural networks and deep convolutional neural networks. In 2014, Microsoft proposed what we call it the ResNet. It was another type of approaches that used a new idea, which is the residual or the skip connection, let's say, type of implementation. So we need to go deeper. Now, what's the problem with going deeper? It's very well known that when you stack together a lot of number of layers, as you increase the number of layers, you'll get the performance. You expect to have the performance to be increasing, but the actual situation is not like that, because you'll get some problem with the what you call it. We just mentioned the vanishing gradient problem or the exploding gradient problem, where we want to calculate for the back propagation the gradient. You will find that either this gradient will be going very small and close to zero or almost zero, or it may be rising to a very high value, and this means that the gradient is increasing, which means that the weights are going to diverge. So in these situations, you need to invent something new in order to control the performance of the system, and to go deeper and increase the performance while not being stuck with such situations. Now, as I just mentioned, it's not easy just to stack more layers together to get the output. If you look at these two graphs, here we talk about the training problem in terms of the iterations. Now, as you go further, if you take the let's say more layers, you may get that the error is going to be increased for both cases. When in case of 20 layers or 60 or 56 layers, it depends on the percentage of the training error, and for the testing error, the error will be also increased. Now, it was assumed that, or it was expected to have, when you have more layers, you'll get the error, the training error will be reducing this way. But the actual output was higher than when having only 20 layers. And this is the same thing for when we deal with the testing data. And you see that almost after some iterations, the error will be almost not reducing very quickly, or almost with no reduction in error. And this is why we need to prevent our system from such cases. And this is what was people thinking in ResNet. The invention of ResNet was designed this way. Now, ResNet proposed a tool for building neural networks with a different approach. Here, this approach, what you call the residual network or block, helps us to build neural networks or convolutional neural networks that are very, very deep, approaching in theory infinity, but in fact, maybe up to 1,000 layers. Let's have a look on the concept. The concept here was very simple. If you look at this small piece of figure, uh, let's have this pen now. So if you look at the input X from previous layers, and this is the output at this layer, of course, this is the output in this situation. Let's say X dash or X prime. Now, we usually pass this way in all networks, having weighted layers by convolution, by ReLU activation, etc., all these steps. Now, we have added, or they have added, the what we call it, the skip connection. Skip connection. So we bridge the output directly to the input this way. Let's clear all these things. So this connection is bridging the output directly to the input directly to the output. This means that the output will contain the function or the operation that was done on the input at this or at the earlier stage, plus the input itself at this location. This will help us to avoid the vanishing or exploding gradients. Why? Maybe due to your work on the network this way, you may get the gradient being set or going to zero, or maybe going to plus or minus infinity. In this case, you just bridge the output by the skip connection here and provide it to the output. This gives you in the output function or the output of this layer, the value of X. It may be scaled by some scale, but in general, this is the case. So if you want to find the gradient of the spark will be almost considered if you get such a situation, and the main part of the system will be relying on the calculation of the gradient having the value of X. So theoretically, you can repeat this infinite number of times. Once you have the gradient of X is not set to zero or not approaching zero. And this is the main idea or the main benefit behind using the skip connection in the ResNet, and this is why we call it residual or ResNet approach. Okay, and as we have just seen, this is the same thing. Essentially, the residual blocks allow information to flow from the initial layers to the last layers, and because we have many skips, and so this means that we are every time flowing or making the data flow from the input to the output, from input layers to the output, or intermediate stages or layers. Notes, in general, in ResNets, we can see this configuration. If you look at here at these connections here, this is the input from down. It will be applied to the block of the, what we call it the ResNet block, and it will be fed directly to the result or the output of the dotted line block. Then we apply maybe ReLU stage and other next stages on the next layer. Now in this block we have a 3x3 convolution, batch normalization block, ReLU activation function. Then we repeat 3x3 convolution, batch normalization, and get the output. Then we apply the ReLU activation function. In fact, this configuration is very clever and gives you an ability to repeat many times your, let's say, this block many times, and you may reach very, very deep neural and convolutional neural networks. In this situation, if we call the output this location y, this y can be calculated this way. It's the function provided on the steps of having X and the weights obtained from these layers or from these blocks on this layer for sure. Okay. So the the set of W values are the weights obtained from the learnable parameters within this block, the actual block. I mean this one. Okay, let's clean all these things here. So W can be found from this block. The weights are achieved. So if we get some problem with this Wi, the value of y includes also another value of x, which keeps the gradient far away from being vanished or exploded. Now, sometimes if you bridge the output to the input, the input to the output, the size here, maybe the size will not be equal to the size at this point. For this purpose, you can just add 1-by-1 conversion in order to bridge or to keep the size compatible between the input x and the output y. In this case, this is the direction of the Wi, where we have the forward pass, and here we have the skip connection pass, where the 1-by-1 conversion will change the weights within the output, its output, new output, and this will lead to modify the value of W. In this situation, you have the value of y. Y will be based on fxwi as here, but we here add the weights of the effect of the 1-by-1 conversion multiplied by x, and this will change a little bit the values. However, it will still be working very nicely, and you don't care, don't afraid of doing that. We have a lot of resonant variants, number of layers playing, so we can bridge or we can stick together or stack maybe a large number of layers. For example, we started by resonant 18. It's a very well-known network. Adding more layers, 34, 50 layers, resonant 100, 152, and we still have more versions coming these days. And you see here the number of parameters is also increasing. So here we have about 11 mega learnables, 21, 23, 42, etc. As we increase the number of layers, the number of learnables will be higher, and it is expected to have better performance when increasing the number of layers. For sure, it's not very straightforward, but you can, roughly speaking, say that this is the case. This is the architecture of the ResNet 35. You see that here the bridge connections or the skip connections, the ResNets, the residual blocks. As you see that we can do this many times, maybe until we get the final stage, which is the average pooling. This replaced the fully connected layers that were used in previous versions of the CNNs that were published earlier. So the idea now is, I think it's clear. So also a comparison between Resident 34 and VGG 19 and 16. You can see that this is the ResNet with bridges here, and the number of layers is 34 blocks, while this is the plain case without the residual blocks. Of course, this is not used actually. And here we have VGG 19 having the structure. In general, VGG 19 is good in performance, while ResNet is in many times overcomes the VGG 16 and the VGG 19. What are other types or popular networks? As I told you that we have ResNet up to 152. We have also other type is DensNet. This is DensNet. We also have other types like DarkNet. I think we may find here DarkNet. The most interesting are the ResNet XT, this one. It's also very interesting. And ResNet version 2. All these networks are used intensively these days, and you can see many papers and many practical implementations using these networks. What about the data sources, data sets? You can find a large number of data set resources. Maybe you can go to sites like GitHub, and you can find a lot of data sets. Here, one of the, I mean, general or public data sets. You can also find specific data sets for medical applications, for electrical, for communications, for security. All these things can also be found. The first data set that is very usually or very commonly used in last days is the MNIST dataset. It contains, as here, 60,000 examples of samples, and it has around 10,000 tests for in the data set subset. It contains handwritten real-world handwritten data. It can be used for your let's say a deep neural network that you can perform like AlexNet and other functions like LUNet 5, etc. What else? We have also the COCO dataset. It's a large-scale dataset that contains a very rich variety of object detection, segmentation, captioning datasets. So it has the datasets and the ground truth for these samples. So you have the input image, and you have, if you look at here, we can see the images and the let's say the labeling of the objects in the dataset itself for segmentation applications. It contains a large number of images with a large number of around 200,000 labeled features in different images. It has about 1.5 million objects instances, 80 object categories. However, you can have a look on the details regarding this dataset. If you go to, if you just print on the net MS COCO dataset, you'll see the manual or the handouts or maybe a PDF file containing all the details regarding this dataset. I need just to know where to search and see, for example, these datasets. Another dataset is the ImageNet. It's very famous, used for training almost all the popular and well-known neural networks, deep neural networks, and CNNs. It contains around 2 million images with 100,000 phrases in the images, providing 1,000 classes at the output. You can go also and see the more details regarding these dataset and other datasets as well. We can find also the CFAR10. It's very popular, especially in Python. It is used very strongly there. You can find also in MATLAB such datasets like CFAR, COCO, CAFE. That's it. All these can be available with a large number of images combined for animals, cars, planes, etc. All these can be found in, let's say, datasets. Now, this is the main what we can talk about. Of course, we cannot stop talking about new DNNs and new DCNNs, and you can just they are mostly relying on the concepts that are considered or discussed in this lecture. You can go to these links, YouTube links, and see more details about this topic in details. So for the day, that's all, talks. I hope that it was enjoyable for you, and have a good time to listen and to comprehend these ideas and these networks. And hope seeing you very soon, inshallah.